Okay, so we've finished the day off with my dear friend Amin, whom I know since I don't know when. And whenever I have a class I'm teaching and I don't know 5 minutes before how to teach it, I will call Amin and ask him for help. For example, on this theme. So he will take us about spread of information in networks.
Yeah, thanks, Christian. What Christian is not, did not tell you is that he was actually my mentor at my very first internship at Microsoft Research. I won't tell you how long ago, quite a while ago. So
you're saying I'm abusing the fact that I was your advisor?
No, it's always a pleasure to hear from you. I'm wondering if the people at the door are coming in or not. I changed what I wanted to cover quite a bit after Matt's talk. I thought, since he talked about the equilibrium structure on the, sort of games and, sort of a structure of equilibrium, the lattice structure of equilibrium on networks, I'll talk about, sort of some of the connections of that to graph models and stochastic processes on networks. Specifically, I'm going to talk about this, spread of innovations, game dynamics and network structure, and most of it is built on the joint work with Andrea Montanari. So the motivating question is, sort of when you look at the diffusion of behavior or technology in a social network, and I'm going to look at it as the dynamics of the game. I'm going to sort of model it as the best response dynamics of the game on a network, and try to drive the equilibrium of the game, the sort of and the evolutionary dynamics, and then come back to sort of interpret this in the context of social networks. So this pretty much is the same as Matt's last slide. When you think about the sort of a spread of a technology or sort of a behavior in a social network, you can think of it in different ways. For example, you can model it as a contagion process, since that you adopt a technology, an innovation, or a behavior when you come in contact with others who have adopted it. So in that sense, your mental model is that the technology sort of spreads like a virus. Or you can say, sort of, think of it as social learning. So you learn about, sort of the payoff of a, sort of an action through interactions with others. For example, in the context of hybrid corn, you're a farmer, you drive by a farm, you see they have, planted this new type of corn, and it's yielding, better results. And sort of these two are similar to each other. Or you can think of sort of the dynamics as sort of the dynamics of the peer pressure or peer influence. So for a lot of actions, and Matt sort of talked about this, like adoption of a new technology, like sort of whether you're choosing sort of you're on Facebook or on Instagram, you're using Microsoft or sort of a PC or an Apple computer. Or even for sort of that the way you dress, the political party that you're part of, the sort of the religious sort of institution that you're part of, whether you go to a mosque or a synagogue or a church, is influenced by people close to you, in the sense that you have a very strong incentive to conform, to take the same action as sort of people in your social networks. So you think about this as you can model this as the dynamics of a coordination game. Even sort of choosing which side of the road you drive on, you really want to have the same sort of choose the same side as everyone else in your. So I'm going to think of this as a game on a network. the players or the nodes, let's say they can take two actions, +1 or -1. And so xi is the action of node I. And think of it as sort of a payoff matrix. So if you take the action plus and your neighbor also takes the sort of action plus, you get sort of A. This is a coordination game. I want sort of the people to have the higher incentive to take the same action as their neighbors. What this means is that A is bigger than D and B is bigger than C. So when you take an action, you look at sort of everyone else around you, in your social network, what other actions they have sort of taken, and you get a payoff of sort of from each of these interactions. You add it up, that's your total payoff. So here is a simple example. You want to choose a cell phone provider. So, either say plus is AT&T and minus is Verizon. So, if your friend is in the same network as you, you may have a higher payoff because maybe you're not paying for the minutes. Sort of the in-network, if you're talking within the network, sort of it costs you less. And let's say between the two here, as an example, like maybe AT&T has a better reception. It, gives you the newest iPhone. So all things equal, you have a slight, preference for, sort of joining AT&T. So the type of calculation, sort of a node I in the network would make is that it looks at, sort of how many of its neighbors are taking the action plus, how many taking the action minus. The payoff would be, for the plus is 6n plus I plus 2n minus I, and see if the action plus has a higher payoff, you take that. Otherwise, you take the action minus. It's not hard. These numbers are less important. It's not hard to see that there is a threshold. So for every sort of depending on this payoff matrix, if above a certain threshold of your neighbors take the action plus, you take the action plus. Otherwise, you take the action minus. So another way of writing it is that you can say for every I, there is an HI such that the best response is the sign of HI, sum of the XJT J in the neighborhood of I. So you just add up the plus ones and minus ones, and then depending on sort of the payoff matrix, you have to add this HI. And without loss of generality, I'm going to assume HI is bigger than 0. So plus action is a little bit more advantageous. So then you can think about this best response dynamics. People occasionally check their neighborhood and they see, who is doing what, and they may change their action to increase their payoff. And it's not hard to see that, the best response increases this potential function. This is a sort of a potential game. Every time somebody takes the best response and changes its response in, sort of its action in response to the action of its neighbors, this function increases. So that tells you that the best response dynamics converges to an equilibrium, essentially to one of the local optima of this potential function. And the potential function can have, several local optima, so you can have, the game can have different equilibria. Again, we saw that, sort of Matt talked about the, the equilibria having this lattice structure. Yes.
So why local? I thought like if the HIs are all positive, this looks like ferromagnetic, so you would just increase it to all the plus ones?
Well, let's look at this example. So let's say HI is 0.1. Let's say these black nodes are taking the action plus, and the white nodes are taking the action minus. Nobody has an incentive to change, right? These people, sort of, for example, this person has two of his neighbors taking the action plus, 2 are taking the action minus. Plus is slightly advantageous, so it will take the action plus. And a node here has 3 neighbors that are taking the action minus, so it's going to stay in this. So this is one equilibrium. So if you think about the best response dynamics, it stays at this equilibrium. Now, imagine that you have one node that, sort of here, you allow for some noise. So let's say this node, gets too excited about the new iPhone, or for some reason makes a mistake and switches its action to plus. Now all of a sudden, its best response for this two to switch to the action plus. Now, sort of this noise, can, grow this region. It can also shrink it. But in order to shrink it, I will need more than 1% to make a mistake. So if you think, introduce some noise, it actually creates a drift towards the expansion, sort of the new technology, the superior technology, or the, sort of in the jargon of, KMR, the risk dominant action, sort of takes over. Everybody will, sort of add a little bit noise to the system. Everybody will switch from minus to plus. Is that clear?
I had a hole in the middle.
No, the hole, sort of fills in quickly, right? Imagine this vertex is minus.
No, bigger hole.
Oh, still. So imagine, sort of the nodes that are right at the border of the white region inside. The best response is to switch to black to the plus action. So it starts shrinking. So you don't even at the corners, yes. But then once that person switches, the person next to it will switch. Yeah, so even you don't even need to introduce the noise. Sort of the inside will shrink. So this was, sort of observed in the paper by Candori et al. Sort of, but it was seen, sort of, you mentioned the, sort of the Ising model. Also, sort of physics. This is discussed in the sort of named nucleation. Like when you have a sort of soda, you shake it, bubbles form. That's a sort of form of nucleation. So far, so good. Oh. So now, there are sort of different ways to look at the noisy best response dynamics. I'm going to look at it, sort of introduce this noise, in a particular way to make the, sort of the Markov chain easier to analyze. So the dynamics that we're going to look at is going to be asynchronous. So it's, strategy revision at the arrival of a Poisson clock. So once in a while, a vertex wakes up, looks at its neighborhood, and it's going to revise its action. So the probability that it takes the action y is e to the power beta y times this quantity. So it's not too hard to see that, sort of, essentially, this is some sort of a soft max. If beta goes to infinity, it becomes exactly the best response action. You want y to have the same sign as this quantity, right? If beta is smaller, you allow for some error. The nice thing about this, sort of way of doing the, noisy best response is that it defines a reversible Markov chain with the following, sort of a stationary distribution. The, sort of probability of a particular configuration is e to the power beta, and that's the potential function that I showed you. Oof. So it's beta times the value of the potential function. Again, so these are called Logit dynamics or Glauber dynamics in, sort of mathematical physics. Yes?
What's the partial lag in the notation?
What is what?
The partial lag.
Oh, it's the neighborhood of y. So it's the, so this is like the probability that xi takes action y conditioned on the state of its the neighborhood of y.
HI is all positive? Or
yes, I'm assuming that HIs are all positive because everybody is playing the same game. In the sense that, let's say, sort of, if AT&T is better than Verizon, it's better for everybody.
That is HI equal for all I, or it's different for all?
It's different, depends on the degree. Yes, proportional to the degree of error. In the sense that if you have a very sort of large degree and everybody in your neighborhood is taking action plus or minus, you have a much sort of higher incentive to take the same action, just because your payoff is going to be, the difference between the two payoffs is going to be higher. So essentially HI is some fixed value that depends on the game times the degree of error. Is this clear? So why is this important? Because I started from, started from a game, and I looked at the, sort of equilibria of the game, and the game had several equilibria. Now, usually, sort of equilibria is like sort of a game theoretic notion used for prediction. So you want to say if people are, sort of in this game playing, sort of what's going to be a likely outcome. Now, a game with many equilibria, the prediction becomes, sort of harder because which one of these equilibria are going to be selected. So if you just look at, sort of best response dynamics, you could, sort of in that grid, you could be, putting, sort of a small boxes here and there. There could be exponentially many equilibria. But by introducing this noise, I'm essentially selecting for the most stable equilibria. So, so that way you can refine your prediction, sort of refine the notion of equilibrium. Now, sort of, by the way, it's not hard to see that this measure concentrates around +1 vector as beta goes to infinity. Because when beta goes to infinity, essentially, as I said, sort of the measure concentrates around sort of the superior technology. Sort of everybody will be taking the action +1. Right? It's different from beta equal to infinity, right? Sort of in the limit, you sort of sort of your measure concentrates around that state. Now, the sort of maybe the next sort of natural question to ask is that when you look at this dynamics, how long does it take for it to reach to this sort of a stable state in which everybody is taking the action plus? So that's I'll call that the hitting time of sort of reaching this all plus. It's the sort of the time it will take for you to sort of be reasonably sure that you have reached that state.
What's the in the first suit? What's the x?
Oh, yeah, it's sort of the worst case starting point. So if you're at all plus, then you're going to be there. Let's say you started from the minus. Yeah.
Wait, but I don't understand. You still have beta not infinite. So will you not always have fluctuations?
Yes, I have fluctuations, but this is a hitting time. So I'm starting somewhere, and I want to know how long it will take for me to get to that neighborhood, like hit that all plus once. But once I'm at the all plus, I'm going to start moving around. Like the hitting time is a sort of natural, sort of value defined for the advantage. All right, and this is Glenn Allison, sort of shortly after sort of Canary et al. Talked about the time it will take for the dynamics to reach this all plus. And so that's important for the prediction, right? So if the sort of it takes exponential time for you to get to a particular state, maybe you cannot really just say, oh, that's the only equilibrium we're going to care about because it will take a very long time. Yes.
Epsilon in your definition of tau plus, I was expecting that it's instead of e to the minus one, maybe 1 over epsilon.
Yes. I haven't. Yeah. Oh, very good. That's a very good question. So I'm cheating a little bit in the sense that when Ellison and KMR looked at a slightly different dynamics, they looked at the dynamics in which you do the best response action with probability 1 minus epsilon, and you take the wrong action with probability epsilon, and they analyze that dynamics. That dynamics defines a Markov chain, but that Markov chain is irreversible. I'm sorry, yeah, it's not a very nice Markov chain to analyze. But this epsilon is the probability of mistake. And then, sort of distributed of K. So, sort of Ellison, sort of analyzed two, sort of different graphs. One was line to the power K, in which, you put the vertices on a line. Every person interacts with, up to K vertices on the left and up to K vertices on the right. So this is a graph in which you have local interaction, right? You just interact with people around you, and said that, sort of the time it will take to hit all plus is epsilon to the power minus theta of K. And in a complete graph where everybody is interacting with everybody, the hitting time is exponentially less. So essentially, so if you look at the paper, the message there is that if you have a small number of neighbors, or if you have local interaction, you expect that sort of you hit that all plus quickly, But when you have global interaction, like a complete graph, it will take a very long time. Is the statement clear? I know this is the last talk you've been at, sort of.
I kind of expect the opposite.
Oh, good. Yeah, so you expect that, sort of in a well-connected network, the diffusion spreads quickly, and in a loosely connected. Yeah, and that's one of the things I'm going to get to. It is surprising in the sense that it's the opposite of, say, epidemic models. In the epidemic models, when you have high degree vertices, when you have well-connected networks, sort of the virus spreads very quickly. Here, the technology spreads slowly. The new technology, let's say the superior technology, spreads very slowly, and sort of in a well-connected network, and quickly in a loosely connected network. But it's one of the reasons, sort of Facebook or Microsoft, is very hard to sort of compete with, right? Because of a strong network effect. If I come up tomorrow with a sort of social network or instant messenger that's a little bit better than Facebook, instant messenger, it will be very hard for me to get everybody to switch, because like they're all using one thing, and they're talking, sort of using that technology to talk amongst each other.
So is the problem to get to half the population, or is the problem to get to from n-1 to n?
Oh, very good. I'll get to this. It's a very good question. Give me 5-10 minutes, I'll get there. Yes.
Is this result related to the fact that payoffs are not normalized for high degree agents? Like if I'm a very, you explained before, if I'm a very high degree agent and I'm comparing the two options, the more neighbors I have, the more reluctant I am to changing.
Fantastic. So it's a very good question. The question is, are we here talking about the degree or something else? So here you have a low degree graph, and here you have a sort of extremely high degree graph. Is the degree the one that sort of determines the sort of, or it's something else? Like sort of global interaction could mean many things. So the question that I want to sort of address is sort of what you guys are asking, the right question. What is the graph theoretic property that captures the rate of convergence? Good. And and then the second question is so when you look at the dynamics, where does it get stuck? Like is it like the first few steps, the last step? She knows me too well. That's why she says expansion. So this is the goal for today's talk. One, find the graph theoretic property that captures convergence, and then demonstrate on specific graph sequences, specifically expanders, finite range graphs and small words, sort of to demonstrate that. So it turns out that the graph theoretic property that captures the rate of convergence is this sort of tilted cut width. It's sort of, if you sort of have done work in algorithms, it's very related, very close to the notion of cut width of a graph. It says, and I know the definition is a little bit long. Let me sort of parse it. Imagine you have a linear ordering of your vertices. If you order your vertices in some linear order, then you can look at the size of the cut at every sort of prefix. So you can look at the first t vertices, that would give you the subset st. You can look at the number of edges, that's the cut. You have to subtract for this sum of hi in s. That's sort of the sort of the force that sort of that forces you from switching from action minus to plus. So you look at the difference of these two, you look at the maximum overall t, and then you look at the ordering that gives you the minimum of this quantity. That's the tilted cut width. The cut width of a graph is the one in which you draw, you drop this, and you look at the sort of maximum cut over linear ordering. Yes.
This might be a bit or you might not know, but like somebody was telling us yesterday about Morris and contagion and the notion of cohesiveness.
Yes.
So is this tilted cut width
related to that?
Is cohesion?
Yes, it is. So turns out that the Hitting time rate of convergence is exponential in this quantity that I showed you. Essentially, when you look at the gamma slope, you have to look at not just the tilted cockpit of the graph itself, but also all of the subgraphs. And two special cases of our interest are, when h is equal to 0, when the technologies are exactly the same. In your, sort of when you talked about the Ising model, this is when you don't have a magnetic field, and that was sort of a study by Kenyon, Mossel and Perez, and sort of our result is a generalization of that. When you set beta equal to infinity, beta is the the noise, the inverse of the noise. So beta infinity meaning best response dynamics, and that's the dynamics that Morris looked at. You will get, so then you want this to be equal to 0, and that will recover the notion of cohesiveness. Sort of requires a little bit algebra, but it's essentially a generalization of Morris. Yes.
So when you say beta equals infinity, that's convergence law?
No, beta equal to infinity, just like pure best response dynamics. So that's essentially Morris.
How do you get that extreme? You can't get that out of the global dynamics. Can you get something that's spectrum?
Oh, yes. So essentially the limit of beta going to infinity is the same as K and R when epsilon goes to 0. There is a small difference, and the difference is the following. In the K and R, the epsilon is the same for everybody. In this dynamics, if you have a higher degree, the probability that you make a mistake is smaller because the difference between the two pairs is higher. That's the only difference.
Capital gamma was your tilted cockpit?
Yes, that's right. Yeah.
So you say it's little O of beta, but could it be that sort of for some graphs you have to choose beta really huge, and for other graphs beta doesn't have to be that large before it holds?
Yeah, that's a very good question. We don't answer. We only look at the limit.
So you look just for a given finite graph.
Yes.
So for example, if I wanted to know it on ZD,
yeah. So we just look at the limit of noise going to 0 or the beta going to infinity. Yes.
I might be lost here.
Yeah.
So when beta is infinity, there is no noise. And I thought that you relied on existence of noise to say that we do get to this all state.
Yes. Very good point. So beta equal to infinity is different from beta going to infinity. So the limit is different. So beta equal to infinity means there's no noise, right? So then you can get stuck in this local optimum.
I see. So this
but
is
now here, if I introduce some noise, sort of I can get, and then when I make the noise smaller and smaller, I will go to the global optimum. And this is the global optimum of the potential function. And the question I'm asking is that how fast?
I see.
but Morris is better equal.
Morris is, yes, so essentially when beta is equal to infinity, you need this to be, in order for the dynamics to go to O plus, you need this to be exactly equal to 0, which means that you don't have any cohesive group.
You show the definition of tilted cockpit.
Sure. So essentially it says, you always want this to be bigger than the cut. That essentially means that so that recovers the definition of not having a cohesive, a p cohesive.
But how does beta, when you take the beta equals infinity, how do you recover Morris? Like, where does beta?
Yeah, so when you take beta equal to infinity, you want this quantity to be equal to 0.
I see.
So essentially, if you think about this whole notion of getting the stuck in local optimum for sort of in order to go to O plus, essentially it means there is no local optimum. You don't get stuck anywhere. So it means that these are sort of barriers. It means that you have no barriers. You don't have any. You don't get stuck in. All right. Now the proof, and that sort of takes me to Christian's question, is where does this quantity come from? you start from some sort of open configuration, a starting configuration, and you want to go to the all plus. When when you go to all plus, your potential function is at its highest possible value. But when you're at this starting point, you have to first decrease the potential function before you can increase it, right? So think about this example that I showed you on the grid with everybody doing a plus. When somebody sort of made a mistake, I decreased the potential function. So the time it will take is sort of proportional to this, how much you have to decrease the potential function because before you can increase it among all the different paths that go from this starting point to all plus. So you start from your starting point, you look at all the different paths that will take you to all plus, you look at the one that decreases the potential function the least, and that e to the power beta of that length is it determines the rate of the rate of convergence, sort of the heating time. Yes.
So that there should be a single stable for it first, or there could be potentially many peaks.
Yes, there are many peaks and valleys. Right? Like the grid example that I showed you, there are many local. Right? Yes. So this is the best case scenario. So you start from the starting point and say, what's my sort of path that doesn't decrease the potential function, decreases the potential function as little as possible. That determines it is a proof, but that determines the rate of the sort of convergence. The type of proofs that we do are the concept of this Markov chain comparison or Jerome Sickler, we build on that.
In her language, does that mean that this sort of best path will never go through any of the other detracting local minima?
Yeah, so in the limit it doesn't, right? So in the limit that determines the exactly sort of. It will avoid those, yeah. It's also this sort of.
And you still didn't answer quite my question because it's minimum now. So from your picture, I would guess it's sort of more like half or 1/3 or whatever. But since this is a general graph, it could happen when just says one vertex you have changed or it's the last one.
Absolutely. So I haven't answered your question fully, and I'll show some examples. And hopefully that will build some intuition. Let me not get into sort of some of the mathematical details and sort of the dual notion for the tilted cut within the tilted cut. Instead, sort of try to demonstrate this theorem on a specific graph, sort of sequences like expanders that Nicole mentioned, or some other graphs, so we can see the behavior there. So I don't know if I should define it here. I would say a graph is lambda comma delta expander if and only if for every subset S of vertices whose cardinality is less than or equal to delta, the number of edges that are leaving that subset is proportional to the size of the cut, to the size of the subset. So if you take one subset and you look at how many of its edges are going outside, or what fraction of the what the number of edges that are going outside over the cardinality of that set is lower bounded by this lambda. In that sense, I would say it's a lambda expander. And sort of you can have the lambda comma delta. There you only need to check it for subsets of size less than or equal to delta. Now,
the graph is not very segregated.
Yes, exactly. So it means the graph is very well connected. You don't have these clusters that Matt was talking about, sort of the subsets that talk among themselves and they're sort of well connected among themselves, but not very well connected to anyone else. So it turns out that if the graph is an expander, then gamma star is bounded away. So that is essentially gamma star is linear in that. What does that mean? It means that the heating time could be exponentially large. So if you have a bounded degree expander, so if you have, let's say, 5 regular random graph, it won't behave like the 9 to the power 5. So it's not the degree that is important. It's sort of the well-connectedness of the network, or sort of the
with some steps. I mean, if delta is 1/2, it is usually expansion vertex expansion ratio, lambda, or the edge expansion ratio, lambda.
Yes.
Right?
So if your graph is a good expander, it means that it will behave much closer to a complete graph and not continuous or not.
Can you remind me what's the definition of gamma star?
A gamma star is the tilted cut that I was talking about. So remember the rate of convergence was e to the power beta times gamma star. This is the tilted cut that I mentioned. That's this one. So it's the maximum tilted cut over all subsets. Okay. Yes.
You look here for the time. You look at the time to reach all ones.
Yes.
I guess that typically one looks at the mixing time of the Glauber dynamics, which is not reaching all ones. It's just reaching the stationary.
Yes.
Would they be in the same scaling?
Yes, because as beta goes to infinity, your measure constant turns out all one.
Maybe it goes to, but beta is not.
As beta, so in the limit. By the way, if I say 90% or plus, again, a random regular graph, it doesn't really make a difference because the bottleneck is exactly the place where half of your vertices are plus, half of your vertices are minus. That's where you have the worst value of the potential function. So imagine you have let's say you have the random regular graph, you have a good expander. For every single vertex, switching is very costly. But if let's say if everybody is doing minus, for some one person to switch to plus, they're going to switch quickly back to minus, right? In order to and then maybe 2 or 5 or 10 vertices switch to plus, again they switch back. You really need like half of your vertices to switch to plus for everyone else to follow, and the probability of that is very small, is exponentially small. But once you go over that, half of your vertices, then you start, the dynamics will push you to all plus.
This is what I don't understand, why reaching majority of pluses and from that you will get to all pluses quickly, because there's still lots of exceptions.
There's some noise, but you have a very strong drift towards all plus. So you will go to all plus and then you will have some jumps.
The H's are driving it, right?
H is driving it, right? So between the minus and plus is slightly favorable because of the edge.
Yeah.
But,
but favorable so strongly that very quickly you will get reasonably quickly get all pluses. Reasonably graph is large. There's lots of exceptions, right? Somebody by randomness they still win the minus.
Sure. So I guess the story that I told you believe it for the complete graph, right? Because if everybody is interacting with everybody, if more than a certain fraction of vertices switch to plus, then all of a sudden it's best response. Yeah. Now for expand, so my point is that for expanders, it behaves essentially the same way.
Or maybe he just needs a beta so large that your exceptions are so unlikely that it doesn't destroy the outcome.
Yeah. I guess beta is constant in the expanders that we probably wouldn't have, even if you reach the equilibrium fairly fast. But okay, I get it.
We don't have any questions. Yes.
Sorry, I'm a little bit confused. So the hitting time is basically looking at the worst state that you can start for it to.
Yes. Let's say all minus.
Or yeah, all minus, exactly. So you're just saying that like in a good expander, basically like a complete graph, like if you are in the all minus, it's just taking a long time to get to the balance, to get the majority.
Yes.
And that is why, but once you get the majority, it's fine. So all you care about is to get the majority.
Exactly. So you have, like, let's say in the complete graph, you have all minus here and all plus there. Well, in terms of potential versus the other way, right? And then you have to go to this state in which, like, it's like, let's say half and half. The potential function is much lower. So you have to go through this bottleneck to come to the other side. And in order to go through the bottleneck, you need a lot of people to make mistakes or, do this, take this action that's not best response for them. And that's why it takes a very long time.
So I think what the confusion is, right? As long as beta is finite, this finally getting to set of all plus is a little misleading, because even once you're there, you always have fluctuations away from it. And sort of if beta were constant, then you would have a constant number of vertices that will fluctuate. And I think that's what's here referred
But beta is not constant.
Yeah, right. So it's that's why it's sort of for this type of results. So you have to be very careful how you sort of make beta scale with n, and we make beta scale with n in such a way that these things come out nicely, relatively nicely, right? But then you can ask, oh, what about finite beta, or like really finite beta? In that case, I have to worry about not hitting all plus, but I have to define a neighborhood around all plus, and sort of talk about that. But makes things a little bit makes the notation a little bit more complex, but the message is the same. All right, so convergence time is exponential, say, for random regular graphs or power law graphs. So there is so the old result that shows random regular graphs or expanders, power law graphs in preferential attachment, or sort of random graphs with a given the sequence. We know they are expanders. This is a sort of old result, so we know convergence time, hitting time is exponential for them. So even though the degree is bounded, or the average degree is bounded in these cases.
Now I do have a question. Since your beta changes with that, so is it exponentially large? So if beta is infinite,
yeah, so I understand that you have this question about how beta scales with it. It's not the point of my talk. Let's do it offline.
Your beta is infinite. But if your beta is infinite, is it still converged in finite time, or will it also, because once it's infinite,
I see. Right, so if it's equal to infinity, like when you do best response dynamics, you don't necessarily reach the all plus, right? You get stuck in your conductive.
Right.
So I have to introduce some noise.
Very near to infinity. Now my question is, if it gets nearer to infinity, does it take you longer to get to this thing?
Absolutely, right? Because the learning time, the convergence time is e to the power beta, that quantity.
Oh, I see.
Still ask your question. No. Go ahead, please.
Sorry to push on the point of beta, but one more thing was, is it related to how well this cut behaves? Like exactly, like when beta varies between 0 and infinity, does it depend on how basically how big the max cut would be in this case in order to?
Yeah, no, so right. So the rate of hitting time, the rate of convergence depends on data and it depends on the graph. So yeah, the tilted cut width doesn't depend on the graph. So essentially, you can say this depends on the gain and depends on the graph. And the way these two are sort of combined is in this particular analysis e to the power beta. That's the tilted cut width. All right, good. Now this is an expanded graph. Let's look at a graph that is sort of constrained by the some low dimensional geometry, like a d-dimensional grid. So in a d-dimensional grid, what you know is that sort of if you think about a subset that sort of let's say I fix one vertex and look at a ball of radius r around it, the number of vertices inside grows like r to the power d. The number of vertices on the boundary is r to the power d minus 1. So essentially, the size of the cut grows sublinearly, and because of that, we can show that the gamma star is O of 1, right? Because the S of H, the sum of the HI in S, grows linearly. This one grows sublinearly. So eventually that takes over. So what this says is that the convergence time is fast for all finite range graphs. So, d-dimensional grids, as long as your vertices are only sort of you are on some low dimensional geometry, vertices only talk to connected to ones that are close to them. So sort of think of this as the in contrast with expanders. There sort of when you have a type of expander, convergence is slow. Here convergence is fast.
You need that it's sort of this parametric types that there's really an alpha smaller than 1, or do you not need that?
Yeah, no. So if it's bigger than or equal to, if it's linear, then it's bad, and if it's smaller than s to the power alpha, it's there it's a slow here.
What if it's s over log s?
Well, it's bigger than or equal to S over log S for all subsets or for some subsets.
So if you just have this inequality with S over log S.
Yeah. The best thing I would be able to prove is some sort of, it will be exponential in like n over log n. Because for this term to take over the linear term, so I need to make the number of vertices large enough. And off the top of my head, the number of vertices won't be sort of linear, it will be, but still it will be large enough that I won't be getting O of 1. I would be getting something that's sublinear but super constant.
But what is it, even the graph that has behavior like S over log X? It's not this. What's the natural model of the graph? This is natural and the standards is natural and in between is
what? I just take this graph in 2 dimensions, the other direction, and make it complete graph
and
then I adjust the width of the complete graph and the size of your net.
So like the product of
or maybe the width is log n in one direction and the other is n or something.
Because you can construct it, right? So now let's think about let's think about a model in between. So the small word networks are good examples for models in between, where you have the low dimensional geometry, but you have these long range links. So for example, you put vertices on a grid, every vertex is connected to its nearby nodes, but then for sort of pair of vertices U and V, you add an edge with probability proportional to 1 over the Manhattan distance of these d of U and V to the power R. And now this parameter R you can change. If R is 0, then you're essentially sort of every vertex is connected to something uniformly at random far. And as you increase R, you make these edges shorter. So essentially you favor your neighbors that are closer to you compared to the ones that are further away. And then you can say, I'm going to change this R and see what happens. So if R is bigger than or equal to D, essentially when you have sort of short range edges, then the tilted cut width becomes becomes omega of log n over log n. So essentially what happens is that you have this cluster somewhere, you have this community of people who are well connected to each other. And what happens is that they serve as a barrier. They don't let the sort of the switching from minus to plus. It may happen everywhere else, but since these guys are connected among themselves and not very well connected to everyone else, they sort of resist the peer pressure from the rest of the world for the longest time. So they switch last. If R is smaller than D, essentially you can show that the graph is an expander. Therefore, sort of it's going to be exponential. So to sum it up, if you have a d-dimensional finite range network, then your hitting time is constant, or e to the power beta times some constant. In a small word with R bigger than or equal to D, it's e to the power beta something that's logarithmic. This should be a smaller. Then sort of similar to random regular graphs or other type of expanders, the hitting time is going to be exponentially large. That's the sort of summary of what I showed you. Should I wait for a? I'm not going to do it, but this is the smaller.
What about other power law probabilities as a function of distance for small world? Like, what if you did?
Yeah, good question. We didn't do it. No, so these are the examples we looked at. Yes.
To model like computing platforms that exist in which we run out Netflix. Is it so? It's an open-ended question. Yeah. But like, is it possible to let's assume some of the edge are negative and some are positive? Would that give a dynamic that's in equilibrium? Not everything is going to be positive. Like some group are going to be.
Oh, I see. So you're talking about mixed regimes in which sort of some communities are doing sort of taking one action and another community is doing another one. Absolutely. So this is what we see Sort of, for example, with the Facebook and Instagram, sort of example that Matt mentioned, and this could be for two reasons. One is that, sort of, if you are, a 15-year-old, you want to be in the, sort of on the same platform as people at, sort of around the same age. And also you don't want to be on the same platform as, people are, sort of who are, your parents' age. So in that sense, you will see the, sort of the segregation. Like this is, sort of because of this, you will always have disruptions. Like one good example is, sort of the online dating platforms. Every, sort of 5 to 7 years, you have a new one. Especially because people who are younger don't want to be on the platform where people who are older. Sure.
When R is at the critical point like D, shouldn't there be something else going on?
No, this is the interesting thing. So at R equal to D, something very interesting happens, right? So there is this result.
Oh, so he's asking, is one of them strict?
Yes, one of them is a strict. R less than or equal to D is an expander. So when R is exactly equal to the, when you actually see the small word phenomena like that Kleinberg observed, still you have an expander. So you have equality here. You have equality here, but not here. So this is a strict that is smaller. This is bigger than or equal to. No, I'm sorry, yeah. Yeah, so I'm sorry, this is less than or equal to, and this is a strictly, yes, my apologies. The case where you have equality, you have an expander.
Now, Kleinberg had sort of this observation that only at exactly D you have polynomial type algorithms.
Yes.
And if it's not exactly D, you don't have it. So do you see something or some of that phenomena here, some algorithmic thing where you...
No, we don't see that because think about the case that, sort of R is equal to 0 exactly. Right? In that case, what happens in sort of Kleinberg's result is that you have this long, you have all of your links are very long, so you can get close to the destination. But for the last mile, you have a problem because since all the edges are so long, when you get near the sort of relatively close, you have to walk the rest of the way. Like you have to use the sort of the short edges. But here, if R is equal to 0, for sure I have an expander because essentially I have a random. So I don't see that distinction. And sorry if I don't elaborate on Christian's question, but it's about a different result on finding shortest path in a social network, in a network. All right, what was I? So this is, Nicole observed this right away, but this is in contrast with contagion dynamics, where when you have the spread of an infection, the behavior spreads from an infected node to a healthy neighbor, when it's independent, like the contact process, high degree nodes help with the spread of epidemics, right? Or if you have a very well-connected network somewhere in your network, essentially, sort of that when it gets the infection, it contains the infection for a very long time.
You also have this thing, if you have sort of cut, if it's not an expander, then this is actually not true anymore.
No, the statement I made was about high sort of well-connected networks and high-degree nodes. If you have high-degree nodes and if you have well-connected graphs, infections is spread in them quickly.
Yes.
Right?
Here, if it's high degree and it's well-connected,
you essentially you have an expander. Right? So if you have an expander, it means that your heating time is
expanders are bad for you, but good for everything.
Exactly, that's the message. So when let's say you have a product that you sort of want it to be adopted in a social network, you have to think about how is it going to be spread. Is it a spread more like a virus, or does it spread more like the sort of dynamics of the coordination? Okay. Do people use it because they find out about it from their neighbors, or they use it because everyone in their neighborhood, or a lot of people in the neighborhood is going to use them? Like that, there is a sort of a big difference. Let's say you want to, you're a venture capitalist and you want to sort of invest in some upcoming startup. You have to think about sort of how hard it is for sort of competing with the sort of for the new technology to compete with the incumbent technology. And also, oh yes.
Do you know if like the spread of misinformation would fall more in each case?
Yeah, so again, it depends on whether you think people believe it because of sort of because of the
Is it known like more how it goes?
Oh, I see. I don't know. I don't know if the economists and or social scientists, when it comes to the spread of misinformation, should we think of it more as the contagion process or the sort of dynamics of the coordination game? Yeah, hard to say. One of the challenges, and I'll get to this, is that when it comes to sort of this question of influence, maximization, the talk that I was supposed to give was on this. Imagine you have sort of a contagion process, like sort of you see the nodes in your social network, and then the infection spreads, say like a virus. Then identifying a set of influential or central nodes is relatively easy, in the sense that there are good approximation algorithms for it. There's a 1 minus 1 of the approximation by Ken Beckland and Radford, which is a very high impact paper. There is a paper that I think Suraj is going to present in one of the workshops that we show that even sort of choosing your seeds randomly is not so bad. So if you're in this world, and the interesting, sort of the most important, sort of feature is, sort of in, when you're in the contagion dynamics, is that when you look at the probability of the adoption, it has this like sort of diminishing return. It's like concave. The probability that you adopt as a function of the number of friends adopting, sort of is somewhat, sort of as sort of as you have more friends adopting the technology, the impact of the additional person becomes smaller and additional friend becomes smaller and smaller. So here, when you're in the contagion dynamics, the problem becomes relatively easy. You can, sort of give good algorithms for it. But when you have more of this threshold behavior, like, sort of, then, sort of similar to coordination games that I mentioned, then even the problem of, sort of who are the right people to seed becomes very difficult. So it's actually NP hard to give them an O of n to the power minus 1 minus epsilon approximation for it. And I think, sort of Matt mentioned something along those lines that, here you want to spread the seeds. So you want to, sort of find, a few high degree people and, sort of get them to adopt your technology. But if you have a technology that has a very high, sort of, sort of people adopt it because a lot of people in their immediate neighborhood is going to adopt it. Let's say, if I go back to the example of online dating, you cannot have like one person in San Francisco and 5 people in Atlanta and 4 people in New York City using your app, because each one of them will log in and they will not find the people that that they are looking for, so they stop using the app. You want to sort of win sort of college by college, high school by high school. So the type of sort of seeding that you will do will be very different. Like, it's not surprising for that Facebook is spread from sort of college to college, right? It was a very smart strategy. Yes.
For your second point here, solving for the cut width isn't hard, but if I gave you a solution, does this imply or close to optimal initial seed set? So
yeah,
maybe I didn't pose it right. So okay.
Right. So there are 2 questions, right? So one is that I give you a graph. Can you?
That's NP hard.
That's NP
no.
hard.
But if I gave you the solution, so I'm an oracle,
yes,
and I tell you that this is the optimal sequence. Is the hardness the cut width, or is the hardness something else in the dynamics?
I don't know. It's a good question. Yeah. So if you have access to that oracle.
Couldn't you have the situation that they sort of the hardest cut, right? But then you sort of have lower overcuts, which are still hard. And so now you have to give me those as well.
I see.
But that's still an algorithm, right? Keep all the cuts that are high and seed all of them, like go wild.
I see. So you have an oracle, you can ask for the hardest cut and then for the next
and
cut.
for the all the ones that are more than order n.
This is very good because I guess since this is the start of the program, the start of the semester, there are a lot of interesting algorithmic questions related to sort of influencing or controlling sort of a stochastic process on a network. Now, in the case of the spread of viruses, maybe you want to test or quarantine or vaccinate people to sort of make it as small as possible, or you want to sort of in the case of online marketing, you want the product or the technology spreads as sort of much as possible or as fast as possible. Very interesting questions, many of them very challenging. At least in the worst case, you have to sort of make assumptions about the structure of the network. I look forward to talking to you about all of those, and I'll stop here.